Video is sponsored by squarespace.com/Michael Penn. Get 10% off your purchase of a website or domain when you use my link in the description and pinned comment. Today we're going to play a pretty interesting game. We're going to consider a fairly simple initial value problem given by y double prime equals negative y, and y of 0 is 0, y prime of 0 is 1. And we're going to show that the solution to this initial value problem is indeed periodic with period 2 pi. But now zooming out a little bit, there's an obvious solution to this initial value problem, and it is the sine function. So the second derivative of sine is negative sine, that's easy to check. And then sine of 0 is 0, whereas the derivative of sine, which is cosine, evaluated at 0 is 1. But that's not the game that we're going to play. We're going to derive this periodicity without any knowledge of sine and cosine. So let's say we are adept at differential equations, but somehow we've never learned about the sine or cosine function. Okay, so let's see how we might get started. So we're first going to suppose that we've got some function s of x, which is the solution to our initial value problem. So in other words, s of x satisfies these rules over here. Okay, and then next up, let's define c of x to be equal to the derivative of s of x. So of course I'm using s of x because it's playing the role of sine, and I'm using c of x because it plays the role of cosine. But we have to rid our minds of those thoughts and just think that s of x, the only thing we know about it thus far is that it satisfies these equations, and the only thing we know about c of x is it is the derivative of s of x. Okay, so now where might we go from here? Well, let's maybe rewrite this portion, this differential equation portion of the initial value problem a little bit differently. So let's notice the following. We have s double prime of x plus s of x is equal to 0. That's because it satisfies this differential equation, and then I just rewrote some things a little bit. So now from here, what I'll do is I'll take the derivative of this. And so that'll give me the triple derivative of s of x plus the derivative of s of x equals, well, the derivative of 0, which is 0. But let's notice that the third derivative of s of x is simply the second derivative of c of x. And then, well, the first derivative of s is just equal to c. Okay. And then let's also note that we have the following. We have c evaluated at 0 is equal to s prime evaluated at 0, which is 1 by our setup. And then c prime evaluated at 0 is the same thing as s double prime evaluated at 0, which is in turn equal to negative s evaluated at 0 by our differential equation. But then by this portion of the initial value condition, we know that this is equal to 0. Okay, so let's maybe cut out the middle here and see what we have. Let's put it all in a box up here that we can refer to as needed. So we know first of all that s double prime of x equals negative s of x. We also know that s of 0 equals 0, whereas s prime of 0 equals 1. We also know that c double prime of x equals negative c of x. We know c of 0 equals 1, whereas c prime of 0 equals 0. So notice that s and c satisfy the same differential equation. They simply have different initial conditions. So I think that's kind of interesting in its own right. Okay, so next up what I'd like to do is be inspired by the fact that I actually know something about sine and cosine. And maybe the most famous formula that compares sine and cosine is the Pythagorean identity. Sine squared plus cosine squared equals 1. So perhaps we would like to work towards a similar identity based on our functions s and c, which I want to reiterate, at the moment, are only defined in terms of these equations up here. These are the defining equations of s and c. Okay, so like I said, we're going to want to look at s squared plus c squared, and hopefully that will be equal to 1. But since our definition of s and c is built out of differential equations, what we probably want to do is take the derivative here. So let's do that. We'll take the derivative of this equation, and we have to use the chain rule. That'll give us 2s of x times s prime of x, and then plus 2 times c of x times c prime of x. Okay, nice. But now let's see where we can go from here. Well, notice that this is equal to 2 times s of x times, well, s prime is equal to c of x. And then we'll have plus 2 times c of x. But now we'd probably like to rewrite this c prime of x in terms of, well, hopefully s of x, and hopefully negative s of x, so these cancel. Because of course this is supposed to be equal to 1, which means its derivative should be equal to 0. Okay, so let's squeeze in another little calculation right here. Okay, so let's notice that c prime of x is equal to, well, it'll be equal to s double prime of x. But s double prime of x is equal to negative s of x by our differential equation. Okay, so that means we can replace this c prime with negative s of x. And then that cancels to 0. So let's notice we already kind of had that on the board over here when we were checking our initial condition, but it's useful to see it in general right here. Okay, so let's see what we have. We have the derivative of this function right here is equal to 0. But there's only one function whose derivative is 0, and that is a constant function. I guess it's a family of functions. So let's see, that means that s of x squared plus c of x squared equals, I'll just write in here, some constant. Okay, but what constant? Well, luckily we can just take any value of this, and since this is always a constant, it'll always be equal to that value. So which value should we take? Well, all we know is the values of s and c at 0, so we should probably plug in x equals 0 here. And that's exactly what we'll do, but if we do that, we see that we get 0 plus 1 squared, which is equal to 1. So in fact, we have the Pythagorean identity in the end. Also, let's observe, since s of x squared plus c of x squared equals 1, that means that s of x and c of x are each bounded. They have to be between -1 and 1. If they ever got bigger than 1 or smaller than -1, then their sum would be bigger than 1, and that wouldn't work. Okay, so let's summarize that over here. We have -1 is less than or equal to s of x and c of x, which is less than or equal to 1. Okay, so let's gather all of the facts that we have at the top and then move on.
This video is brought to you by Squarespace.com/Michael Penn. Squarespace has raised the bar with their next generation website design system, Fluid Engine. It's never been easier to stretch your imagination online. You can share your stories of your cat, photos of your cat, videos of your cat, and schedule all of your cat content to make your cat work for your cat. For you. Wait, can cat create websites and post photos? Let's start with a best-in-class website template for every category and use case. Add customizing every design detail and multiply all of that by drag-and-drop technology for desktop and mobile devices. Squarespace connects you to vetted tools to extend your website's functionality. Need to announce a sale or send a newsletter? Email campaigns with built-in analytics measure the impact of every send. And speaking of analytics, Squarespace allows you to learn where your site visits and sales are coming from and analyze which channels are most effective. So wait no longer. Get 10% off a website or domain by going to the link on your screen, the description, and pinned comment. Now back to whatever problem I was working on.
Okay, so here's a summary of everything that we've got so far. So we'll come back to that as needed. Now I'd like to look in at the fact that we have s of x and c of x are bounded. But any function that's bounded and smooth, I guess we didn't assume over here that it's smooth, but let's do that now. Any function that's bounded and smooth has a radius of convergence for its Maclaurin series to be infinite. So that means we could simply replace these functions by their power series. And then that's exactly what we'll do right here. We'll do this with c of x, but it will follow for s of x as well. Okay, so let's first note that c of x equals c of x. So that's of course true. And then we have c prime of x is equal to negative s of x. We derived that on the last board. And then we also have c double prime of x equals minus c of x. So that follows from the first derivative, but let's also recall that it is one of the differential equations that c satisfies. Okay, so now let's look at the third derivative. So the third derivative will be the first derivative of c, but that'll give us a minus s, canceling with this minus sign, giving us positive s of x. And then we have the fourth derivative of c is back to c. Now, since we're all familiar with cosine and sine, and we know that these are really just avatars for cosine and sine, this is really no surprise. But that being said, it's interesting to see that this follows so quickly. Okay, so what do we really get out of this? Well, the 4nth derivative of cosine evaluated at x is simply cosine of x. And the 4n plus second derivative of cosine of x is negative cosine of x. Now we can extend this to see that the 4nth derivative of c of x is equal to c of x. And then the 4n plus first derivative of c of x is equal to minus s of x. And then the 4n plus second derivative of c of x is equal to negative c of x. And then finally, the 4n plus third derivative of c of x is equal to s of x. And then I think what's most important for our purposes is if we evaluate this at 0, we'll get a positive 1 for the 4nth derivative, a negative 1 for the 4n plus second derivative, and then zeros elsewhere. Okay, but that means by the Taylor series expansion formula, we have the following. So we have c of x is equal to the sum, as n goes from 0 up to infinity, of minus 1 to the n over 2n factorial times x to the 2n. So I'll let you recall what the rule from Maclaurin series is, but this follows from all of these like derivatives that we've just calculated. Now let's write out a couple of terms. So this will be 1 minus, let's see, x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial, ... So notice it's an alternating series. And since it's an alternating series, we can truncate it somewhere. And if we truncate it before a minus, we end up with something larger. But if we truncate it before a plus, we end up with something smaller. Okay, so now let's note the following. So we know that c of 0 is equal to 1 by our previous calculation. Now let's look at c of 2. So that's clearly going to be 1 minus 4 over 2 factorial plus 16 over 4 factorial minus 2 to the 6th, let's see, what is that? 64 over 6 factorial ... But like I said, if we truncate it before a minus, we're going to end up with something larger. So that means I can put my inequality in this direction, cut out this minus 64 over 6 factorial and everything bigger, and the inequality follows. So this is going to be less than 1 minus 4 over 2 factorial plus 16 over 4 factorial. And then you can easily check that that is equal to negative 1/3. Okay, so now let's see what we have. We have c of 0 is equal to 1, that's a positive number. C of 2 is equal to negative 1/3, that's a negative number. So what does that mean? So by the intermediate value theorem, there is some theta which is between 0 and 2 such that c evaluated at theta is equal to 0. So as you go from 1 to negative 1/3, you have to pass through the x-axis, and that'll be our 0. Okay, and then furthermore, let's take the smallest one of these. So a priori, we don't know that there aren't a ton of these between 0 and 2 that are roots of our function. So let's just take the smallest one. Okay, and then from this, it follows, using the Pythagorean trig identity, that s evaluated at theta must be equal to 1. So again, that's by this Pythagorean trig identity. You might say that it could be plus or minus 1. Well, I'll leave it as a little bit of a homework exercise of why we can take it to be the positive 1. Okay, great. So let's maybe bring that information up, and then we're pretty close to the end. Okay, so now I've recorded that up here. Theta is the smallest positive number such that c of theta was equal to 0. So before we said it was the smallest number between 0 and 2, but that immediately makes it the smallest positive real number. Okay, so now let's take a general solution to just this differential equation without the initial value. So let's write that up here. So the general solution of y double prime equals minus y must be a linear combination of s and c. And that's because, well, let's recall we know a lot about differential equations, we just don't know anything about the sine and the cosine function. So we know that the solution space of this should be two-dimensional, and we found two linearly independent functions that satisfy this. Okay. So that means we could write down a general solution, and let's do that. Y is equal to a times s of x plus b times c of x. But now let's make another little observation, and that is the following function, s of x plus t, also satisfies this, what I'm going to call the defining general differential equation right here. But then since s of x plus t satisfies this differential equation, it must be of this general form. So that means we can write s of x plus t as a times s of x plus b times c of x. And now we need to determine a and b. And it stands to reason that they should probably depend on t. And we'll see the first dependence on t by setting x equal to 0 into this first starting equation and see what happens. So that's going to give us s evaluated at t is equal to a times s of 0, which is 0, plus b times c of 0, which is 1. So we have s of t is equal to b. Okay, so let's hold on to that. And now we somehow need to figure out what a is. And we can get that by taking the derivative of this equation and then, playing the same game. So the derivative of s is c, so that's going to be c of x plus t equals, derivative of s is c again, so we have a times c of x, and then it'll turn into minus b times s of x because of our derivative rules. And now we'll play the same game. So let's set x equal to 0 again and see what happens. So that's going to give us c of t over here equals a. Okay, nice. So now we've determined our two coefficients a and b. We're really in terms of t and our original functions. So let's write that down. We have s of x plus t must be equal to, I'm going to write it in the order s of x times c of t, and then plus s of t times c of x. So something like that. And then using extremely similar techniques, we can get c of x plus t is equal to c of x, c of t, minus s of x, s of t. So I'll let you determine that on your own. Okay, so now let's bring those two facts up here, and then I think we have all the tools we need to finish this off. Okay, so we finally finished our fetch quest in order to finish this thing off. That is show that we have a period of 2 pi on our function, well, that's a solution to this, which is the function s of x. Okay, so how might we go about finishing it off? Well, let's take this sum formula for s of x, and we'll set x equal to x and t equal to theta. Of course, like setting x equal to x means we're not changing anything, but we'll just like point that out. All we're doing is setting t equal to theta here, recalling that c evaluated at theta is 0. Okay, so that's going to give us s of x plus theta is equal to, well, s of theta. So s of x times c of theta, which is 0, plus c of theta plus s of theta, which let's recall we knew that that was 1, and times c of x. So this is c of x in the end. So immediately we've got this like kind of shift rule between the s function and the c function. And now let's play the same game here. So let's branch this yellow thing off, and now we're going to set x equal to x and t equal to theta in there. And let's see what that'll give us. So that'll leave us with c of x plus theta is equal to, well, we've got another c of theta here, which is 0, and then a minus s of x, s of theta. Recall that s of theta was 1. We mentioned that much earlier, but we haven't used it since. So that's going to be minus s of theta. Okay, good. But now we're just going to roll these two things together, and that's going to give us the following. So let's maybe look at s of x plus 2 theta. So maybe to be really clear, we would write that as s of x plus theta plus another theta, and then use this rule right here. So let's see, that's going to give us c of x plus theta. Okay. But now we can use this rule right here, and we'll get negative s of x. Okay, so that means s of x plus 2 theta is minus s of x. Okay, well that really gives us some motivation to do the following. S of x plus 4 theta, so that's going to be negative s of x plus 2 theta using this rule right here, which is equal to s of x. Again, using that rule right there, and the two minus signs cancel. Okay, so let's see what we have. We have s of x plus 4 theta is equal to s of x. And we have c of x plus 4 theta is very, very similarly equal to c of x. Okay, nice. So that combined with how we chose theta up here to be the smallest positive number that makes this happen means the period of s of x and c of x is 4 times theta. Okay, well, I mean, that seems kind of helpful, 4 times theta, but I said over here that it's going to be equal to 2 times pi. And now here's where I'm going to use a little bit of a cheat, just so that we don't go down another rabbit hole. I think you'll forgive me for that. And I'll point out the following, and that is that an equivalent definition for the number pi over 2 is as the smallest positive root of the equality of the power series n equals 0 to infinity of minus 1 to the n over 2n factorial times x to the 2n equals 0. In other words, the smallest positive root of c of x. So like I said, that's an equivalent definition of pi over 2. Okay, but then that's exactly what we took our theta to be. So that means theta is equal to pi over 2 by the equivalence of this definition. Okay, but then putting this together, we see that our period is equal to 4 times pi over 2, which is 2 pi. And there we have it. So just to reiterate what we've done here, we started with an initial value problem and nothing else. And we showed that the solution to this is periodic with period 2 pi without any former knowledge of the trigonometric functions. And that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.